Hello everybody, another Henstitute Help video right here. So this one is our merry-go-round problem. So the idea of this one is momentum conservation. So if I kind of break it down into the main stuff, we know that the initial angular momentum should equal the final angular momentum. The only thing that's a little bit weird here is we have two things that are going through angular momentum. We have the merry-go-round itself, so this object is going around in a circle, but also we have this kid that's on here, and they are also going around in a circle at that same omega I. So I need to kind of break those down. But the first thing I'm going to do is I'm going to point out how do I find the I for the merry-go-round, and how do I find the I for the kid? So the merry-go-round is just a big solid disc. So we talked about this when we ran it down the ramp, that a big solid disc is just 1/2 mr squared. That's not going to ever change. So for the merry-go-round, this would just be 1/2 the mass of the merry-go-round, which is 175, times the radius of the merry-go-round, which is 2.4 meters. So 2.4 quantity squared. And that's going to stay the same because the merry-go-round doesn't change. So that's going to be a key. I'm going to actually write this IMGR so that we can kind of see it. But this is how we would calculate it. The kid is going to be a little bit different. He is like a point mass going around in a circle like this. And so the I for that is actually just mr squared, where r is going to be how far he is from the center of this merry-go-round. So in the first case, the initial for the kid would actually be his mass, which is 50 kilograms, multiplied by the fact that he's all the way on the outside. So it's going to be the 2.4 squared. But later on, the kid is going to change his position. So he's going to move from here into this position. So now he's only this r away, which is 0.6. So his I is going to be 50 times 0.6 squared. Okay, so check, check. That's what we've got. Now, if I come back to what we were talking about earlier, that the initial momentum equals the final momentum, how do I find those things? So the initial momentum is going to be the I initial for the kid times their initial angular velocity. Now I know it's 24 RPMs. You can leave it as RPMs if you want to, or we can change it. So if I was going to change RPMs into radians per second, what we would do is we would multiply it by 2 pi, because that'll change it to radians, and we would divide by 60, because that'll change it from minutes to seconds. So we can do that if we want to, or we can leave it as RPMs. I don't really care which one. The other part that we have is we also have the I for the merry-go-round, MGR, and its initial. So we actually know everything to find the initial momentum of the kid and the merry-go-round. Afterwards, now we have the final I for the kid. So that's the number that we found over here. And then his final angular velocity. Well, this is what we're after. We want to know what this is. So I'm going to just call it omega F. But we also have the merry-go-round, the I for the merry-go-round times its omega F. Hey, that's the same thing. We're trying to find both of those. So the easy way we can do this is we could actually factor this omega F out. So we would have omega F, that's what I'm after, times the sum of their angular velocity, or their moments of inertia. So it would be the final for the kid plus the I for the merry-go-round. So we have everything over here. We can figure out all this. We just don't know what omega F is. And once you do that, you've got it solved and you've got omega F. If you start with it as 24 RPMs, you're going to get a final omega that's going to also be RPMs. If you change it to radians per second, then you'll get a final omega that will be radians per second. Either one is perfectly acceptable because you're setting momentum equal to momentum. As long as the units are the same, things will work out. Hope that helps.